I am delighted that you are with me this evening. Our voyage tonight will lead us to the very core of the stars, the immense furnaces of the cosmos. These radiant spheres of plasma are far more than simple, faraway glimmers of light. Some possess a scale so vast they could consume our entire solar system. Others implode into minute remnants that revolve hundreds of times each second. And each and every one is a cosmic foundry, forging the elements that constitute our bodies, our planet, and all that we perceive. When we gaze upon the nocturnal sky, we are effectively peering back through history. The starlight that reaches our eyes this evening might have begun its journey hundreds, thousands, or even millions of years in the past. A portion of those stars may have already ceased to exist, their light serving as the final echo of their former presence. Yet others are destined to radiate long after our own world has vanished. If these serene explorations resonate with you, please consider showing your support with a like and subscription, or perhaps leave your thoughts in the comments. This gesture helps other weary travelers find this haven as well, one soul at a time. For this moment, however, you have no obligations. Simply find your comfort. Allow your breath to deepen and let your mind drift into a state of weightlessness. If you are prepared, let us commence. The most massive stars discovered could engulf Earth's orbital path entirely. Certain stars are of a magnitude that simply boggles the mind. The red hypergiant Ui Scuti, for instance, boasts a radius exceeding 1,700 times that of our Sun. If it were positioned in the center of our solar system, its periphery would extend past the orbit of Jupiter. Even more modest supergiants like Betelgeuse or VY Canis Majoris would utterly swallow the orbit of our planet. These colossal stars are quite uncommon, consuming their fuel at a rapid pace and surviving for only a few million years, in contrast to the billions of years afforded to more ordinary stars. Their distended atmospheres are volatile, casting off material into the cosmos in vast clouds that drift away like cosmic smoke. The sheer immensity of these giants serves as a reminder that our own Sun, while enormous by our terrestrial standards, is rather small compared to the truly gigantic suns scattered across our galaxy. Certain stars radiate with such intensity they can surpass the brilliance of whole galaxies. While the majority of stars shine with a familiar glow, select rare behemoths, known as quasars and hyperluminous stars, are capable of emitting more energy than the collective light of billions of suns. Stars such as Eta Carinae, a luminous blue variable, unleash so much energy that they can match the brightness of entire small galaxies. During a period in the 19th century, Eta Carinae erupted with such ferocity that it temporarily became the second brightest star in the night sky, despite being situated over 7,000 light-years from us. Stars of this caliber live precariously, burning through their hydrogen fuel at an incredible rate and frequently culminating in an explosive supernova. Their tremendous light exerts such strong outward pressure that it strips away their outer layers in potent winds, forming the radiant nebulae that envelop them. These celestial beacons remind us that a single star, for a brief cosmic moment, can hold dominion over its surrounding cosmos. Following the cataclysm of a supernova, a neutron star can be formed from the collapsed core. When a gargantuan star concludes its existence in a supernova, its core can collapse into an extraordinary object, a neutron star. These entities measure only around 20 kilometers in diameter, but possess a mass greater than that of the Sun. The collapse compresses atoms with such force that protons and electrons fuse into neutrons, yielding matter denser than any other substance known, save for that within black holes. A mere teaspoon of material from a neutron star would weigh billions of tons. Their surfaces are solid, their gravitational pull is immense, and their magnetic fields are beyond imagination. In spite of their diminutive size, they are visible across the cosmos, either by projecting beams of radiation or by warming their vicinity with residual energy. Neutron stars are the phantoms of stars, the collapsed hearts of once mighty suns that are now spinning, dense relics challenging our comprehension of matter. They reveal the incredible extremes to which the universe can stretch the principles of physics. A subset of neutron stars, known as pulsars, rotate with astonishing velocity, completing hundreds of revolutions each second. Within the family of neutron stars, some exhibit an even more remarkable characteristic. Referred to as pulsars, they spin at incredible speeds, often achieving hundreds of rotations per second. With every turn, they project beams of radio waves or light across space, which we perceive from Earth as a consistent pulse. The most rapid pulsars, termed millisecond pulsars, can spin over 700 times in a single second, a rate faster than the blades of a household blender. These pulses are so regular that astronomers employ them as cosmic timekeepers, measuring them with an accuracy surpassing atomic clocks. The initial discovery of pulsars in the late 1960s even led to speculation that they might be signals from extraterrestrial beings before their true physical nature was understood. Today, pulsars are instrumental in verifying the predictions of Einstein's theory of relativity and are even used in the search for gravitational waves undulating through the universe. They stand as some of the most dependable lighthouses in the cosmos. An unusual variety of neutron star, the magnetar, possesses magnetic fields of unimaginable strength, powerful enough to tear atoms asunder. Magnetars are a peculiar type of neutron star characterized by their magnetic fields, which are the most potent known in the universe. A magnetar's field can reach up to 1,000 trillion times the strength of Earth's. This level of power is nearly beyond comprehension. It would be sufficient to warp atomic structures, dismantle molecules, and reconfigure matter itself. When their magnetic fields undergo a sudden shift, magnetars can emit gigantic flares, releasing more energy in a split second than our Sun does in hundreds of thousands of years. These energetic bursts have been observed from immense distances, at times briefly outshining all the stars in our galaxy combined. Thankfully, magnetars are scarce, and none are situated close enough to endanger Earth. They function as extreme cosmic laboratories, demonstrating what occurs when physics is pushed past the boundaries we can replicate on our world. Not every star is a perfect globe. Rapid rotation can cause a star to bulge at its equator, resulting in a flattened, oblate form. When a star revolves at an exceptionally high speed, centrifugal forces cause its equatorial region to expand outward, squashing it into an oblate shape. A well-known case is the star Achernar, which spins so fast that its diameter at the equator is 50% greater than its pole-to-pole diameter. Such swift rotation can eject material into space, creating gaseous disks around the star. These misshapen suns challenge our conventional image of stars as round, balanced spheres. Instead, they show that stellar existence can be dynamic and agitated, shaped by rotation as much as by mass and age. Stars that spin rapidly might also circulate their internal material more efficiently, thereby extending their lifespans relative to their more slowly rotating counterparts. From a distance, they glitter like any other star, but up close, they are wildly distorted by the unceasing force of their own velocity. Among the most volatile and ephemeral stars are hypergiants, which can shed more than our Sun's total mass annually. Hypergiants are some of the most unstable and short-lived stars in the cosmos. Their vast size has a significant drawback. They consume their fuel with such ferocity that their outer layers are unable to remain gravitationally bound. Consequently, they lose mass through powerful stellar winds, shedding more than the entire mass of our Sun in just a few thousand years. Eta Carinae, one of the most celebrated hypergiants, is enveloped by an enormous nebula formed from material it has expelled into space. These storms of gas and dust enrich the galaxy with elements that can later coalesce into new stars and planets. For the hypergiant itself, however, this process is one of self-destruction. Its destiny is almost certainly to detonate in a spectacular supernova, possibly even forming a black hole in its wake. These stars are cosmic infernos, both magnificent and destructive, illustrating the extremes of stellar potential. A star that wanders too near a black hole is destined for a violent demise. The black hole's tidal forces, the difference in gravitational pull between the star's near and far sides, stretch it like a piece of taffy. If the star gets too close, it is ripped asunder in a cataclysm known as a tidal disruption event. The stellar matter then spirals inward, creating a brilliant disk as it is consumed by the black hole. This event unleashes a flash of light that can momentarily outshine all the stars in an entire galaxy. Occasionally, jets of this material are ejected outward at nearly the speed of light, broadcasting the event's destructive power across the universe. While these events are infrequent, they offer astronomers a method for studying black holes that would otherwise remain unseen. Each one is a cosmic spectacle, a luminous star shredded by the ultimate force of gravity. When astronomers detect sudden, powerful bursts of light from galactic centers, they might be observing a star's destruction by a black hole. These tidal disruption events happen when a star moves within a black hole's gravitational influence and is stretched beyond all recognition. The star's substance creates an accretion disk, which heats up to millions of degrees and glows in X-ray and ultraviolet light. These flares can persist for months or even years as the black hole consumes its stellar meal, slowly fading as the star's remains are pulled in. By observing these phenomena, scientists can determine the mass of black holes and gain insights into galactic evolution. They also act as stark reminders that even stars, immense, radiant, and long-lasting, are not immune to the more profound forces that govern the cosmos. To witness one is to get a glimpse of gravity's raw, insatiable appetite. The merger of two stars in a tight binary orbit can generate some of the most spectacular phenomena in the cosmos. Neutron star mergers specifically emit energy not just in the form of light, but also as ripples in the very fabric of space-time known as gravitational waves. These waves propagate outward at the speed of light, alternately stretching and compressing space as they travel. In 2017, astronomers detected gravitational waves from such a merger, which was subsequently followed by bursts of gamma rays and visible light. This marked the first instance where humanity observed both gravitational waves and light from a single cosmic event. These collisions are also responsible for forging heavy elements like gold and platinum, seeding the universe with the materials that eventually form planets and support life. Every ripple of gravitational waves that we detect is a message from stars colliding at unimaginable distances. Not all stars are confined to their native galaxies. Some are catapulted outward with such force that they escape into the immense void between galactic clusters. These rogue stars can be set in motion by violent occurrences, such as a close pass by a supermassive black hole or the chaotic dissolution of a star cluster. Once they are ejected, they drift through the cosmic emptiness, taking any surviving planets with them into an unimaginable solitude. Envision a lone sun, billions of years removed from its origin, journeying endlessly without a galaxy to call its own. Although they are challenging to spot, astronomers theorize that there could be countless intergalactic stars scattered about like embers carried from a great fire. They serve as a reminder that space is not a static environment, but is filled with motion and contingency, and that even an object as massive as a star can be set adrift on the cosmic ocean. In the primordial universe, long before galaxies formed, the initial generation of stars came into being. Astronomers refer to them as population 3 stars, and they were likely colossal, some being hundreds of times more massive than our Sun. Lacking heavy elements to cool the gas clouds from which they formed, these giants grew swiftly and burned with an incredible intensity. Their lifespans were probably only a few million years, a mere flicker on the cosmic timeline. Upon their demise, they exploded as monumental supernovae, enriching the universe with the first atoms of carbon, oxygen, and iron, the fundamental components for planets and life. None of these first-generation stars exist today, but their influence is still visible in the ancient chemical compositions of the cosmos. By analyzing these clues, scientists are reconstructing the narrative of how the first light broke through the darkness, transforming the universe from a void of hydrogen into a place capable of sustaining life. When a star like our Sun concludes its life cycle, it leaves behind a hot, dense core known as a white dwarf. Initially, these stellar remnants radiate brightly, glowing from the residual heat of their former nuclear reactions. However, over billions and trillions of years, they gradually dissipate that energy, slowly fading into obscurity. The ultimate state is referred to as a black dwarf, a cold, lifeless star that no longer produces light. As of now, none exist. The universe itself is not yet old enough for even the most ancient white dwarfs to have cooled to this extent. The concept of black dwarfs pertains to the distant future, an era when the cosmos will be a more tranquil and darker domain. They signify the ultimate fate of countless suns, a silent monument to the fact that even the most brilliant stars must eventually yield to the passage of time. Should the universe expand indefinitely, its far-flung future could be one of encroaching darkness. Stars will eventually deplete their fuel, and new ones will cease to form. Red dwarfs, the most slowly burning stars, might continue to glow for trillions of years, but they too will ultimately dim. Galaxies will become faint, planets will turn to ice, and the night sky will be devoid of starlight. In this scenario, sometimes termed the heat death of the universe, the cosmos grows cold and silent, populated only by black holes and the faint remnants of extinct stars. Although this future is unimaginably distant, the idea is both sobering and strangely serene. The saga of the stars has a commencement and a conclusion, and we are fortunate to exist in a time when the sky is still ablaze with their light. To look upward now is to see a universe still in its brilliant, star-filled youth. While our universe might be fated to grow dark, certain cosmological hypotheses propose this isn't the final chapter. Concepts from cosmology suggest our universe might undergo a bounce or spawn entirely new universes. In those new beginnings, the stellar cycle could begin anew. The elements created in our universe might serve as the seeds for the next, preserving continuity across cosmic epochs. Just as stars die and distribute the components for new ones to form, universes themselves could follow a similar pattern of collapse, rebirth, and renewal. Though this is highly speculative, it presents a vision where starlight never truly goes out. Instead, it transitions across scales far grander than we can readily comprehend. From this perspective, the stars above are not merely a feature of our universe, but part of a potentially endless cycle, an eternal ballet of light and regeneration. Not every star has a brief, brilliant existence. The smallest, known as red dwarfs, consume their fuel so efficiently they can shine for trillions of years, a duration far exceeding the current age of the cosmos. These stars are dim and cool in comparison to our Sun, frequently invisible to the naked eye from Earth. Nevertheless, they are by far the most prevalent type of star in the universe, constituting the bulk of suns in the Milky Way. Due to their extreme longevity, red dwarfs could support planets where life has an abundance of time to arise and evolve on timescales we can barely imagine. None of them have yet entered their old age, as the universe is still too young. This implies that the night sky of the distant future will still be illuminated by these small, persistent embers long after more luminous stars like our Sun have faded away. As the cosmos matures, the most luminous and massive stars will be the first to extinguish. Blue giants and hypergiants last for mere millions of years. Stars like the Sun endure for billions. But red dwarfs, those small, efficient stellar bodies, persist for trillions. Over these vast timescales, they will become the primary sources of light in the universe. The galaxies of the remote future might glow only with their soft red light, creating a gentler and more solitary sky. In time, even these long-lived stars will exhaust their fuel, transforming into white dwarfs and finally into black dwarfs. The universe will transition from a bright, star-filled domain to one illuminated only by dying embers. It is a vision of cosmic dusk, where the last stars burn quietly, ushering the universe into its concluding phases. For the present, we are living in its golden era, surrounded by brilliant suns of every size and hue. In the hearts of galaxies, supermassive black holes, weighing millions or billions of times more than the Sun, hold court. Remarkably, stars can orbit directly around them, following paths that push the boundaries of gravity. In our own Milky Way, astronomers have tracked stars speeding around Sagittarius AI, the black hole at our galactic center. One such star, S2, comes within a mere 17 light-hours of the black hole, an infinitesimally small distance on a cosmic scale. At its closest point, it travels at over 5,000 kilometers per second. Tracking these orbits enables scientists to calculate the black hole's mass with exceptional accuracy and to validate Einstein's theories about how gravity warps space-time. These stars endure in a region where one might expect them to be destroyed, demonstrating that even in the shadow of a black hole, the celestial dance of starlight can persist. An encounter with a black hole doesn't always lead to a star's annihilation. Sometimes it is ejected at incredible velocities, propelled by the immense gravitational force. These hypervelocity stars can attain speeds of millions of kilometers per hour, fast enough to break free from their home galaxy. The Milky Way is home to several such runaway stars, which are now racing outward into intergalactic space. Their journeys likely started near Sagittarius AI, where interactions with the central black hole functioned like a gravitational slingshot. For any planets that might be orbiting such a star, the outcome would be extraordinary. A solar system cast away, speeding through the cosmic darkness alone. The discovery of these stellar castaways shows just how dynamic galaxies can be and how black holes influence not only what is drawn in, but also what is thrown out. What appears to the unaided eye as a solitary point of light is often a system of 2, 3, or even more stars gravitationally bound. Binary stars are particularly widespread, with two suns orbiting a common center of mass. Some pairs are so close that they transfer matter between them, whereas others are so distant that they complete an orbit only once every few thousand years. For a person on a planet within such a system, the sky might showcase 2 or 3 suns rising and setting in unison, creating multiple shadows. A famous instance is Alpha Centauri, our closest stellar neighbor, which is a triple star system. By examining these pairs and groups, astronomers can learn more about how stars are born and how they evolve. What often seems to be a lone light in the night sky is frequently a hidden family of stars, orbiting together in a long and elegant dance. When a massive star concludes its life as a supernova, it doesn't merely vanish. It profoundly alters its cosmic neighborhood. The explosion sends shock waves through nearby clouds of gas and dust, compressing them and initiating new cycles of star formation. In this manner, the demise of one star can lead to the birth of many others. Our own Sun might have been formed from such an event, its natal nebula enriched with heavy elements dispersed by a prior generation of giant stars. These cycles guarantee that galaxies stay fertile with starlight, continuously recycling matter into new configurations. Every brilliant star that perishes leaves behind more than just remnants. It leaves the seeds for future suns, planets, and possibly even life itself. Stars do not simply end, they pass on their legacy, igniting the subsequent chapters in the ongoing saga of the cosmos. While the majority of stars that go supernova do so in a final, definitive explosion, a few defy this norm. In exceedingly rare instances, a massive star might erupt with great force, survive the initial blast, and then explode again years or even decades later. These peculiar events are known as pulsational pair instability supernovae. The star becomes unstable, ejects vast quantities of its mass, and then temporarily restabilizes, only to collapse completely at a later time. Such stars shine with unpredictability, creating multiple bright outbursts that can lead astronomers to believe they are observing repeated supernovae in the same location. These exotic stellar deaths underscore the diversity of fates for massive stars and reveal how much we still have to discover about the limits of nuclear fusion and stellar instability. In cosmic terms, they are stars that seem reluctant to fade away, leaving a dramatic, flickering testament to their struggle against gravity's final, inexorable pull. A specific category of stellar explosion, the type Ia supernova, shines with a remarkably uniform luminosity. These events happen when a white dwarf star in a binary system accretes too much material from its partner, triggering a runaway thermonuclear detonation. Because these explosions consistently occur at approximately the same critical mass, their maximum brightness is nearly identical throughout the universe. This consistency makes them standard candles, dependable beacons that astronomers utilize to measure cosmic distances. By comparing their apparent brightness from Earth to their known intrinsic brightness, scientists can determine how far away they are. Type Ia supernovae were instrumental in one of astronomy's most significant discoveries, the accelerating expansion of the universe propelled by dark energy. They are not just spectacular stellar demises, but also essential measuring tools that help us comprehend the vastness of the cosmos itself. Every atom of precious metals like gold and silver, as well as essential elements like iron and calcium, was forged within a star. When massive stars detonate as supernovae, they eject these heavy elements into space, enriching the interstellar medium. Over eons, this material is incorporated into new stars, planets, and living organisms. If not for supernovae, the universe would be a far less complex place, primarily composed of hydrogen and helium. Instead, each explosion plants the seeds of complexity. The iron in your blood and the calcium in your bones were once propelled outward by such a blast, drifting through space before being incorporated into Earth. Supernovae are violent conclusions, but they are also new beginnings, scattering the building blocks of life far and wide. In this respect, stars are both creators and destroyers, ensuring that the universe is filled not only with light, but also with richness and diversity. While it might sound like poetry, it is a statement of scientific fact. The very atoms composing your body were created inside stars. The oxygen you inhale, the carbon that makes up your cells, the iron coursing through your blood, all of it originated in stellar cores and supernovae. Billions of years ago, before Earth was even formed, those elements were adrift in space, waiting for an opportunity to coalesce. Carl Sagan famously remarked, "We are made of star stuff," and this phrase encapsulates a deep truth. Every person, every plant, every rock is an assembly of recycled stardust. When you raise your eyes to the night sky, you are not merely looking at distant suns. You are witnessing your own cosmic origins. The stars provided the fundamental materials, and in return, we represent the universe gaining consciousness of itself. The connection between us and the stars is direct, literal, and profoundly humbling. Stars generate energy through nuclear fusion, combining lighter elements into heavier ones. This process creates energy, but only up to a certain element. When a star's core starts to fuse silicon into iron, the dynamic shifts. Fusing iron does not release energy. On the contrary, it consumes it. This signifies that once iron builds up in a star's core, fusion can no longer counteract the force of gravity. At this point, collapse is unavoidable, resulting in a catastrophic implosion and frequently a supernova. The formation of iron is a death warrant for massive stars, signaling the moment their fuel has been fundamentally exhausted. It is extraordinary that this common metal, so ubiquitous on Earth, also serves as the cosmic fulcrum that determines when giants of light must ultimately fall. A star maintains its form through a precise equilibrium between two competing forces. Gravity attempts to pull all of its mass inward, seeking to crush it into a dense core. Meanwhile, fusion, the conversion of hydrogen to helium at its center, pushes outward with heat and radiation. For as long as these two forces are in balance, the star remains stable. If the pressure is too great, it expands. If it is too weak, it shrinks. Our Sun has sustained this balance for billions of years and will do so for billions more. However, when the fuel in its core is eventually depleted, the equilibrium will be broken, and the Sun will evolve into something entirely new. This cosmic tug-of-war is the essential reason why stars exist as steady sources of light instead of instantly collapsing or tearing themselves apart. Fusion is not merely the source of a star's light, it is the very force that prevents its immediate implosion. Without the outward pressure of energy from fusion, gravity would crush a star into a dense, collapsed object in a matter of moments. Even our Sun, with its placid yellow light, is balanced on this razor's edge every second. The continuous fusion of hydrogen into helium prevents it from collapsing under its own colossal weight. For more massive stars, this balancing act is even more pronounced, with incredible forces at play. When fusion ceases, gravity invariably triumphs, compressing the star into a white dwarf, a neutron star, or a black hole. Stars can only exist as long as fusion persists. Their light represents a fragile triumph over the relentless inward force of gravity. Not all stars burn with the same measured pace as our Sun. The most massive ones devour their nuclear fuel at incredible rates, sometimes up to 1,000,000 times faster. This means that despite being much larger and more powerful, they lead extraordinarily short lives, occasionally lasting just a few million years. In contrast, our Sun is expected to shine for about 10 billion years. These fast-burning giants radiate with a brilliant blue light, injecting energy into space and influencing their galaxies with powerful radiation and stellar winds. Their brief lives end violently, often in supernovae that enrich the cosmos with heavy elements. The disparity between them and stars like our Sun demonstrates how size determines fate. The larger the star, the shorter and more spectacular its existence. They are cosmic spectacles, brilliant but transient, while smaller stars persist as steady beacons across the expanse of deep time. Our own Sun, while currently stable, is destined for a spectacular transformation. In approximately 5 billion years, it will have used up the hydrogen in its core. As fusion transitions to helium, the internal balance will alter, and the Sun will expand immensely, becoming a red giant. Its surface will grow outward, likely consuming Mercury and Venus, and possibly Earth as well. The Sun's outer layers will radiate a faint red glow, much cooler than today's golden light, while its core will shrink and heat up. Eventually, these outer layers will drift off into space to create a luminous planetary nebula, as the core contracts to become a white dwarf. Although this change lies far in our future, it serves as a reminder that even stars like our own are temporary, following trajectories dictated by the physics of fusion and gravity. Our familiar star will one day become something completely different. From our vantage point on Earth, no star shines more brightly in the night sky than Sirius. On a clear evening, Sirius commands the celestial sphere. Also known as the dog star, it glows with nearly twice the brilliance of the next brightest star, Canopus. Some of its brightness is due to its intrinsic luminosity, but its relative proximity, at only about 8.5 light-years away, makes it appear particularly radiant from our perspective. Ancient civilizations observed Sirius for thousands of years, associating it with myths, calendars, and navigation. In ancient Egypt, its appearance in the dawn sky signaled the annual flooding of the Nile. Today, astronomers recognize that Sirius is, in fact, a binary system composed of the bright Sirius A, a hot white star, and Sirius B, a faint yet dense white dwarf that was once a massive star itself. To the naked eye, they merge into a single, piercing point of light. Sirius is not just bright. It's a reminder that appearances in the night sky often conceal more complex stories. Long before the invention of the telescope, humanity bestowed names upon the most prominent stars in the sky. These names held significance related to agriculture, navigation, or mythology. Stars like Betelgeuse, Rigel, and Aldebaran have names that originate from Arabic traditions, while Vega and Altair derive from ancient Arabic and Latin. In China, India, Greece, and Egypt, stars were integrated into narratives that helped societies interpret the heavens. Even now, these ancient names persist, linking us to people who observed the same sky millennia ago. Behind every familiar constellation is a rich tapestry of human history, with names handed down through various languages and cultures. While modern astronomers use catalog numbers for greater precision, the old names continue to echo through time. They remind us that our connection to the stars is not solely scientific. It is profoundly cultural, reaching back to the very dawn of civilization. Prior to the development of compasses and GPS, the stars were mankind's most dependable guides. Polynesian navigators traversed the Pacific by memorizing the rising and setting positions of stars, guiding their canoes across thousands of kilometers of open ocean. The North Star, which remains nearly stationary in the sky, has long been a reference point in the northern hemisphere for determining latitude. Arab merchants, Greek mariners, and Viking adventurers all depended on the celestial map to direct their travels. Even the seasonal movements of people and animals were often synchronized with the positions of the stars. These skills were transmitted orally, with songs and stories containing entire star charts. Navigating by the stars demanded exceptional memory and keen observation, but it was effective. Long before modern technology, humans relied on starlight to guide them safely to new destinations. The same stars continue to shine above us today, though we now view them with a sense of wonder rather than out of necessity. Polaris is renowned for being the North Star, a seemingly fixed point around which the heavens turn. However, it has not always occupied this position, nor will it do so indefinitely. Earth's axis undergoes a slow wobble, a motion known as precession, which completes a cycle approximately every 26,000 years. This means the identity of the pole star gradually changes. Around 3000 BCE, the star Thuban in the constellation Draco served as the marker for true north. In about 12,000 years, the brilliant star Vega will assume this role. Polaris is merely the current holder of the title in a long history of shifting skies. Ancient structures, such as some pyramids and stone circles, were aligned with different stars that once held the position of the northern celestial pole. Observing the change of the pole star is like watching the Earth take a slow breath over millennia, a reminder that even the patterns we rely on in the heavens are in constant flux. If you were to stand upon the surface of a distant exoplanet, the familiar constellations would disappear. Stars appear to be grouped together from Earth solely because of our specific viewpoint. Observed from light years away, their configurations would change into unrecognizable patterns. On a planet orbiting Proxima Centauri, our Sun would be just another faint star in the sky. From the Andromeda Galaxy, the Milky Way itself would look like a glowing spiral, and the stars we know would be lost within its arms. This change in perspective demonstrates that constellations are illusions created by distance and angle. The night sky is not a static canvas, but a three-dimensional ocean of suns that looks different from every possible vantage point. To envision other skies is to appreciate how profoundly our perception of the universe is influenced by our location within it. The star patterns we recognize, like Orion, Cassiopeia, and the Big Dipper, are merely temporary arrangements. Over thousands and millions of years, stars drift through space, their positions shifting relative to one another. Gradually, the familiar shapes will distort beyond recognition. The hunter Orion might lose his belt, the Big Dipper might lose its handle, and entirely new groupings will form. For us, these changes are too slow to be perceived in a single lifetime, but on cosmic timescales, the sky is in a state of constant transformation. Future civilizations, or even different species, will inherit skies filled with entirely new maps. The mythology of their constellations will be unique to their era, just as ours are linked to ancient cultures. The constellations we see tonight are but snapshots of a fleeting configuration, a reminder that nothing in the cosmos is permanent, not even the patterns we trace among the stars. Gravity has the power to bend light, a concept predicted by Einstein and since verified. When the light from a distant star travels near a massive object like a galaxy or a black hole, it can be warped and amplified. This effect is known as gravitational lensing. At times, it can divide a star's light into multiple images or make it appear significantly brighter than it actually is. Astronomers have even seen individual stars magnified in this way, making them briefly visible from billions of light-years away. Without this lensing effect, those stars would be undetectable. Nature's own magnifying glass enables us to look deeper into the universe than our instruments alone could. It shows us that space is not a void, but a flexible medium, capable of bending light in ways that uncover hidden cosmic wonders. Even the journey of starlight is influenced by the unseen hand of gravity. Constellations are fundamentally human constructs, patterns we impose on the celestial sphere, but they are not everlasting. As the Milky Way rotates and stars move on their individual paths, some of today's most well-known shapes will cease to exist. In approximately 50,000 years, Orion will no longer have its familiar form, as its bright stars will have dispersed across the sky. In a few million years, the Big Dipper will not resemble a dipper at all. To future observers, these constellations may not exist in any recognizable form. Just as ancient people saw different skies than we do, future beings will inherit their own unique celestial patterns. The constellations we know are simply transient alignments, and our myths are connected to a passing arrangement of stars. They remind us that the sky itself has a history, and the maps we create of it will one day be as obsolete as ancient nautical charts. Although they seem static, stars are in a state of perpetual motion. Their vast distances make this movement nearly imperceptible to the naked eye, but over centuries and millennia, the changes become significant. This gradual drift is known as proper motion. Barnard's star, for instance, visibly shifts against the background stars every few decades, exhibiting the fastest known proper motion of any star in our sky. Comparing ancient star maps to modern ones reveals this slow rearrangement of the heavens. Even the shapes of constellations have subtly changed throughout human history. This ever-shifting sky reminds us that what appears eternal is not. The stars are not fixed points on a celestial dome. They are suns traveling through the galaxy, each with its own trajectory and history, their light tracing paths of motion across cosmic time. Our sun is not stationary. It completes an orbit around the Milky Way's center roughly every 200 million years. Throughout this journey, its stellar neighborhood changes. Stars that are close to us now will eventually drift away, to be replaced by others crossing our galactic path. In the distant past, the sun's nearest neighbors were completely different, their light mingling with ours in a different night sky. As it continues its voyage, the constellations around us will transform, and the stars we are familiar with will fade from our perspective. This cosmic movement illustrates that even our sun's position is temporary, part of a grand rotation that carries us around the galaxy. To look at the sky is to see just one moment in an unending journey where our stellar companions come and go over the ages. Orbiting the peripheries of galaxies are globular clusters, dense, spherical collections of stars, often containing hundreds of thousands, packed into a relatively compact area. They circle the outskirts of galaxies like sparkling satellites, each one a relic of the early universe. Many globular clusters within the Milky Way are over 12 billion years old, nearly as ancient as the universe itself. Their stellar populations are typically composed of small, faint red dwarfs and long-lived giants, as any massive stars they once had burned out long ago. When observed through a telescope, a globular cluster appears as a brilliant snowball of light, with stars so densely packed in its center that they seem to merge. These clusters are more than just beautiful. They are windows into the past, revealing how the first stars formed and lived. Studying them is like reading a history book written in starlight, one that chronicles the earliest days of our galaxy. Scattered amongst the younger stellar populations of our galaxy are a few true veterans, ancient suns that formed close to the dawn of creation. Some are more than 13 billion years old, almost as old as the universe itself. These stars were born from primordial gas that contained very few heavy elements. Astronomers can identify them by examining their spectra, the unique signatures of elements in their light, and finding patterns nearly unchanged since the Big Bang. While such ancient stars are rare, they provide clues about the initial moments of star formation before galaxies had fully developed and the cosmos was enriched with heavy elements. To observe one is to peer into deep time, connecting with a survivor from an era when the universe was still young and dark, just beginning to be illuminated by the first starlight. Galaxies are not static. They can collide, merge, or be disrupted by gravitational interactions. Yet the stars within them can endure these transformations. A star that formed in a small galaxy might find itself incorporated into a larger one, following a galactic merger where it will continue to shine for billions of years. Some stars might even be ejected into intergalactic space, destined to wander alone long after their home galaxy has dissolved. In this way, stars can survive events that obliterate the very structures that gave them birth. It is a reminder that stars are both creations of galaxies and independent objects, persisting long after galactic boundaries have shifted. These solitary survivors are cosmic witnesses, having lived through upheavals on scales almost too vast to comprehend, their light outlasting the cosmic cradles that first ignited them. Not every star exists in a clean vacuum. Some are enshrouded by peculiar shells of gas and dust that were expelled from their surfaces during times of instability. These shells can create luminous rings, arcs, or bubbles illuminated by the star's radiation. The causes for this vary. Some stars lose mass via powerful stellar winds, while others experience eruptions that cause them to temporarily expand and shed their outer layers. Often, this material contributes to intricate nebulae, forming beautiful and sometimes enigmatic patterns. In certain instances, astronomers observe multiple shells, indicating that a star has undergone repeated episodes of mass loss. These gas shells do more than just adorn the stars. They enrich the galaxy with elements that will eventually form new stars and planets. To study them is to observe a star in the midst of transformation, wearing its history in radiant veils. A rare and incredibly unstable class of massive stars, Wolf-Rayet stars, burn with such intensity that their outer layers are blasted away by powerful stellar winds. These winds can carry off more than 10 Earth masses of material each year, forming spectacular halos of gas and dust around the star. Their exposed cores radiate with intense heat, often reaching temperatures exceeding 50,000 degrees C. Wolf-Rayet stars are thought to be in a transitional phase, leading short, violent lives before they either explode as supernovae or collapse into black holes. Despite their scarcity, they have a significant impact on enriching galaxies with heavy elements. Their turbulent winds and eventual explosions distribute the raw materials for new worlds. They are stars living on the brink, burning so fiercely that they cannot endure for long, blazing with intensity before their certain end. As a star travels at high velocity through interstellar gas and dust, it can generate a bow-shaped shockwave ahead of it, analogous to the wake created by a boat. These bow shocks are visible in infrared light, where astronomers can detect them as arcs or crescents preceding the star. They reveal both the star's motion and the density of the medium it is traversing. Such stars are often runaways, having been ejected from their birthplaces by explosions or gravitational interactions. Their glowing wakes are transient, existing only while the star is passing through gas-rich areas. Each bow shock is like a frozen wave in space, a luminous footprint that marks a star's restless voyage across the galaxy. Not all stars remain bound to the stellar nurseries where they were born. Certain stars are ejected from their clusters or galaxies at velocities reaching hundreds of kilometers per second. These runaway stars can be propelled by supernova explosions that send them flying, or by gravitational interactions with massive black holes. In the most extreme instances, they attain a hypervelocity sufficient to break free from their home galaxy's gravitational pull entirely. For any planet circling such a star, the outcome would be remarkable: a solar system thrown alone into the cosmic void. Though uncommon, runaway stars illustrate the chaotic nature of the universe, where stellar lives can be abruptly displaced by powerful forces. They traverse the galaxy like cosmic castaways, serving as a testament that even stellar bodies are subject to the unpredictability of gravity's influence. The most nascent stars are frequently concealed by dust. Newly formed stars seldom make an immediate appearance. They come into existence within dense clouds of gas and dust, the leftover matter that collapsed to create them. These dusty cocoons obstruct visible light, shielding the stars from conventional telescopes. To bypass this, astronomers employ infrared and radio observations to penetrate the obscurity, uncovering clusters of protostars that are still in the process of accreting mass. Frequently, these young stars are encircled by disks of material that might eventually form planets. Over time, radiation and stellar winds disperse the dust, allowing the stars to emerge and shine without obstruction. Observing a nascent star is akin to watching creation unfold, a brief and fragile phase that constitutes only a small portion of a star's existence. Protostars glow even before nuclear fusion commences. A star does not initiate its existence by instantly igniting fusion. Prior to that point, it exists as a protostar, a concentrated mass of gas contracting due to gravity. As it shrinks, its core heats up, and the protostar emits a soft glow powered solely by gravitational potential energy. Throughout this phase, which can extend for hundreds of thousands of years, the star accretes material from its surroundings, increasing in size and temperature. Jets of gas often emanate from its poles, signaling its presence within the dark clouds of its formation. Only when the core temperature climbs to about 10 million C does hydrogen fusion ignite, officially transforming the protostar into a star. This concealed period is the universe's quiet prelude to starlight, a time when the future of a sun is still being constructed from darkness. Brown dwarfs blur the distinction between planets and stars. Not every celestial body can be clearly categorized as either a star or a planet. Brown dwarfs exist in the ambiguous space between these two classifications. Too substantial to be considered planets, but lacking the mass to sustain steady hydrogen fusion like a true star, they radiate faintly with residual heat from their formation. Some undergo a brief period of fusing deuterium, a heavy isotope of hydrogen, before diminishing into dim, cool bodies. Brown dwarfs can be difficult to detect, as they shine primarily in infrared light. However, astronomers have located many of them drifting independently or orbiting other stars. They showcase the variety of celestial objects the universe is capable of producing, thereby challenging our classifications. In a way, they are failed stars or perhaps oversized planets, reminding me that the cosmos often defies straightforward definitions. It is possible for stars to combine, creating even more massive suns. Stars are not invariably solitary. When two stars orbit in close proximity, they can spiral inward and coalesce. Such events unleash immense quantities of energy, occasionally resulting in spectacular eruptions that are visible throughout the galaxy. Upon merging, the stars typically become larger, hotter, and less stable, with new layers of nuclear fusion igniting within their cores. Some mergers might even form rare star types that could not arise naturally, such as blue stragglers, stars that seem unusually young because they have been revitalized through the merger process. These occurrences can also leave behind disks of material that may either give rise to new planets or simply dissipate into space. Although violent, stellar mergers are a component of the cosmic life cycle, reshaping stars into new configurations. They serve as a reminder that the lives of stars are not isolated, but are instead interconnected, shaped by their neighbors and fortuitous encounters. Within many binary systems, one star expands at the cost of its partner. As stars age and grow into giants, their outer atmospheres can be drawn by gravity onto the companion star. This transfer of mass can profoundly change the fates of both stars. The recipient star might become hotter and more luminous, while the donor is stripped down to its core, sometimes leaving a white dwarf behind. In extreme scenarios, the acquired mass can push a star beyond its stability limit, causing a nova or even a supernova. These interactions generate some of the most spectacular phenomena in the heavens, from flickering variable stars to immense explosions. Binary stars are cosmic plunderers and casualties, their lives entwined in relationships as intricate and dramatic as any myth, but enacted in light and fire over millions of years. Some stars do not merely exist in pairs, they form trios engaged in complex gravitational ballets. Triple star systems can be configured in various ways. Two stars in a close orbit with a third circling farther away, or all three interlocked in elaborate, shifting arrangements. These systems can generate chaotic gravitational influences, affecting the movement of any planets that may orbit them. In certain instances, planets can be forced into highly inclined orbits, where they experience the rising and setting of multiple suns. Triple systems are fairly prevalent, demonstrating the universe's penchant for variety. To observe one through a telescope is to glimpse an alien solar system quite unlike my own, where the cadences of day and night would be entirely different from anything on Earth. Such stars show that the conventional solar system I inhabit is merely one possibility among many peculiar cosmic configurations. Science fiction frequently envisions worlds with two suns, and astronomy has verified their existence. Planets can follow stable orbits around binary stars, circling both suns concurrently. In such a system, a planet would undergo complex diurnal cycles with dual sunsets and varying light patterns. Other planets orbit just one star in a binary pair, with the companion star rising and setting like an exceptionally bright moon. NASA has confirmed the existence of several such circumbinary planets using the Kepler telescope, establishing that these exotic setups are real. Life under multiple suns would be governed by cycles unlike anything on Earth. Seasons, illumination levels, and even shadows could behave in unpredictable ways. These systems broaden my understanding of what is feasible, reminding me that the diversity of planetary environments is far greater than my imagination once conceived. Not all stars are distributed uniformly throughout galaxies. Some are born in massive collections. Star clusters can contain hundreds of thousands of suns concentrated within a relatively compact area of space. Globular clusters, for instance, are so compact that stars at their centers might be separated by only a fraction of a light year. In such settings, stars frequently engage with one another, swapping companions or disrupting planetary systems. Open clusters, which are less dense and younger, often gleam with hot, luminous blue stars, their brief lifespans underscoring the youth of the group. To view a cluster through a telescope is to witness an entire stellar community shining in unison, a reminder that many suns commence their existence not in solitude, but within crowded stellar nurseries. Over time, clusters gradually break apart, their constituent members drifting away to merge with the broader galaxy. Some clusters are billions of years old. While open clusters disperse within several hundred million years, globular clusters persist. Many are over 10 billion years old, rendering them almost as ancient as the Milky Way itself. Their durability stems from their compact structure, with gravity binding their hundreds of thousands of stars firmly together. Over eons, the most luminous stars perish, leaving behind red giants and dense remnants, while faint red dwarfs continue to shine steadily. These clusters orbit the galaxy like artifacts, survivors from an epoch when the Milky Way was still in formation. Analyzing them provides insights into the initial conditions of galaxy formation and the chemical composition of primordial stars. They are cosmic time capsules that preserve information about an era that has long since passed. To look at a globular cluster is to look back across nearly the entire history of the universe. In contrast to their globular counterparts, open clusters are comparatively delicate. They form as collections of dozens to thousands of young stars, often inside expansive stellar nurseries. Over hundreds of millions of years, gravitational forces from the galaxy gradually pull them apart. Ultimately, the stars scatter into the galactic disk, blending in with the general stellar population. My own sun is believed to have originated in an open cluster approximately 4.5 billion years ago, which has long since dissolved. Although temporary, open clusters offer a glimpse into stellar youth, filled with hot, massive stars that light up the surrounding gas in vibrant colors. They demonstrate that stars are not born in isolation, but as siblings, companions for a time before dispersing throughout the galaxy to follow their individual paths. While galaxies like the Milky Way produce stars at a consistent rate, some experience such intense periods of creation that they are termed starbursts. In these settings, stars are born at rates up to 1,000 times higher than normal. Entire regions flare with newborn clusters, their collective light erupting like cosmic fireworks. Starbursts can be initiated by galactic collisions, where tidal forces compress enormous quantities of gas into new stars. Though impressive, these phases are brief on a cosmic timescale, lasting only tens of millions of years. Eventually, the galaxy depletes its gas supply, and the starburst subsides. These galaxies reveal that the universe's rhythms can differ dramatically, sometimes tranquil, sometimes explosive, but perpetually creative. They remind me that galaxies are not static assortments of stars, but evolving, dynamic entities. Stars are formed within giant molecular clouds, which are immense reservoirs of gas and dust that can extend for hundreds of light years. Inside these areas, gravity gradually draws material into clumps that contract into protostars. Telescopes show these nurseries as luminous nebulae, where young stars shine against the clouds that gave them life. The Orion Nebula, which is visible even without a telescope, is one of the closest examples, teeming with hot, massive stars that illuminate their environment. Within such nurseries, entire generations of stars can emerge together, forming clusters that subsequently disperse. To peer into a stellar nursery is to observe creation in action, the fundamental components of the universe coming together to form suns that might one day illuminate planets, and perhaps even life. These clouds are the wombs of the cosmos, shaping the future skies of galaxies. As new stars accrete mass from collapsing gas, many emit focused jets of material from their poles. These stellar jets can extend for light years, impacting the surrounding clouds and creating glowing pathways. This process is thought to help control how a star gathers matter, directing excess energy outward while the remaining gas falls inward. When viewed with powerful telescopes, these jets look like fine filaments glowing in pinks and blues, illuminated by shock waves from their collisions with nearby gas. Known as Herbig-Haro objects, they are some of the most stunning sights in astronomy, vibrant indicators of stellar infancy. Although they persist for only a few tens of thousands of years, they encapsulate the drama of star formation, a brief yet remarkable phase before a star achieves long-term stability. Certain stars do not radiate a constant light, they pulsate rhythmically, alternating between brighter and dimmer states. These pulsating variable stars expand and contract in cycles, propelled by fluctuations in pressure and temperature within their outer layers. Some, such as Cepheid variables, are so consistent that they serve as cosmic timepieces, with their periods directly linked to their inherent brightness. By timing their pulses, astronomers can determine their true luminosity and use them as distance markers across the cosmos. Others, like RR Lyrae stars, pulsate more quickly, but fulfill a similar function in mapping the galaxy. To the unaided eye, these stars might seem to shimmer strangely, but with careful observation, their beating hearts become apparent. Their steady rhythms reverberate through space, transforming stars into natural chronometers and aiding me in charting the immensity of the cosmos. I often consider fire to be the hottest phenomenon I know, but stars surpass even my most intense flames. White stars, such as Sirius A, radiate at temperatures of 10,000 degrees C or higher, much hotter than the bluish flame of burning gas here on Earth. Their surfaces are so intensely hot that they emit light across a broad spectrum, appearing a brilliant white or bluish-white to my eyes. These stars are typically more massive and younger than the Sun, burning through their hydrogen fuel at a faster rate. Their luminosity makes them easy to locate in the night sky, yet their lifespans are comparatively short when measured against cooler stars. When I see a white star shining down, I am witnessing energy on a scale completely beyond terrestrial fire, a fusion furnace so hot that even the idea of flames seems insignificant in comparison. Despite their fiery appearance, red supergiants are remarkably cool by stellar metrics. Their surfaces can be as low as 3,000 degrees C, cooler than my Sun's 6,000 degrees C. However, what they lack in heat, they compensate for in sheer size. Stars like Betelgeuse can expand to hundreds or even over 1,000 times the radius of the Sun, their massive atmospheres extending far into space. If Betelgeuse were placed at the center of my solar system, it would reach beyond the orbit of Mars. These stars are approaching the end of their lives, swollen giants on the verge of an eventual supernova. Their red glow in the night sky signifies both immensity and fragility. Although cooler at the surface, they burn with ferocious intensity inside, determining their final fate as some of the most dramatic stellar explosions in the universe. My Sun may seem central and exceptional to me, but on a cosmic scale, it is a rather conventional, medium-sized star. Classified as a yellow dwarf or G-type main-sequence star, it burns consistently, being neither particularly massive nor particularly faint. Billions of stars similar to the Sun are scattered throughout the Milky Way, each one potentially hosting planets. The Sun's ordinariness is its strength. It is massive enough to sustain fusion for billions of years, but not so large that it burns out prematurely. It offers a stable, long-lasting environment for life to arise and develop. When I look up at the stars, it is reassuring to know that my own Sun is not an anomaly. If life exists elsewhere in the galaxy, it might well orbit a star much like mine, steady, yellow, and dependable. In this context, ordinariness may be precisely what makes it extraordinary. Although they are dim and challenging to see with the naked eye, red dwarfs are by a wide margin the most numerous stars in the universe. Small, cool, and efficient, they constitute perhaps 3/4 of all stars in the Milky Way. Their faint red light ensures that none are visible from Earth without telescopes, despite their prevalence. Because they consume their hydrogen so slowly, red dwarfs have lifespans of trillions of years, far exceeding the current age of the universe. This longevity makes them intriguing candidates for hosting habitable worlds, as any planets around them would have more than ample time for life to emerge. They are the quiet workhorses of the cosmos, vastly outnumbering the bright blue giants that capture my attention. The galaxy's shimmering tapestry is primarily composed of these small, enduring suns. At the opposite extreme from red dwarfs are the blue giants, stars that are dozens of times more massive than the Sun. They burn so intensely that their lifespans are a mere few million years, disappearing in a cosmic instant. Their rarity is a consequence of this brevity. Although many may form, they perish quickly, leaving only a few scattered across the galaxy at any moment. While they live, they shine with astonishing brilliance, often visible over immense distances. Their ultraviolet radiation molds entire regions of space, ionizing gas clouds and creating bubbles in the interstellar medium. These stars are the fireworks of the cosmos, spectacular, short-lived, and impossible to overlook. To observe a blue giant is to witness a rare, transient phenomenon, a cosmic titan that will soon collapse in one of the most dramatic deaths imaginable. Stars do not just shine in white or yellow. Their light encompasses a full spectrum of hues, from deep crimson to icy blue, which depends on their surface temperature. Some stars radiate in colors so subtle that my eyes cannot fully register them. To me, they might all look bluish or whitish, but through scientific instruments, their true colors are revealed. Ultraviolet stars shine with energies my eyes cannot perceive, while cooler stars radiate in the infrared, invisible without specialized sensors. I, as an astronomer, measure these colors using spectroscopy, which separates starlight into its constituent rainbow, disclosing its temperature, composition, and movement. In reality, the night sky is far more colorful than it appears, painted with shades that lie just beyond human perception. The stars I see are only a glimpse of a much richer palette, hidden from my sight, but blazing across the universe in light of every kind. A star's color is not merely aesthetic, it serves as a stellar thermometer. The bluer the star, the hotter its surface. Blue giants can have temperatures of tens of thousands of degrees, whereas red dwarfs radiate at only a few thousand. Yellow stars, like my Sun, are situated in the middle. This principle, known as Wien's law, enables astronomers to approximate stellar temperatures simply by analyzing their light. Telescopes fitted with filters can measure the balance of colors, providing accurate readings. The rainbow spectrum of starlight also uncovers information about a star's composition, motion, and age. Every star's story is encoded in its color, a direct translation of heat into hue. The next time I notice a faint red glow or a sharp white sparkle, I will remember that I am looking at a thermometer written in starlight, a cosmic code that astronomers have learned to decipher. Stars exist across a broad spectrum of masses, with the smallest ones having the longest lifespans. Low-mass stars consume their hydrogen slowly, converting it to helium with exceptional efficiency. Unlike massive stars, which burn through their fuel in just a few million years, these smaller suns can shine for trillions of years without depleting their reserves. Their cooler temperatures make them dim, often invisible to the naked eye from Earth. Nevertheless, they are the dominant stellar population in the galaxy. These stars seldom die in dramatic explosions. Instead, they gently fade into white dwarfs, concluding their lives in quietude. Their longevity and stability make them compelling targets in the quest for habitable planets. Though they may be unimpressive in brightness, low-mass stars are the patient custodians of time, shining long after more luminous stars have extinguished. The cosmos began with only the most basic elements: hydrogen, helium, and a small amount of lithium. Everything heavier, carbon, oxygen, nitrogen, silicon, iron, and more, was created inside stars. Within their cores, nuclear fusion combines lighter atoms into heavier ones, constructing the chemistry of life atom by atom. When stars die, they release these elements into space, where they are integrated into new stars, planets, and living organisms. The oxygen in my lungs and the carbon in my cells were formed in stellar furnaces billions of years ago. Without stars, there would be no rocks, no oceans, no DNA. Each element heavier than helium bears the mark of a star that lived and died before me. To examine the periodic table is to read the history of starlight inscribed in the matter of all that exists. When a star passes in close proximity to a black hole, the interaction can be catastrophic. Tidal forces elongate it, and in many instances, the star is completely torn asunder. Yet sometimes, against all probability, the star endures. In these grazing encounters, the black hole removes only a portion of the star's outer layers. What is left continues to orbit, damaged but whole, often remaining distorted or unstable. I, as an astronomer, refer to these survivors as zombie stars because they bear the scars of near annihilation yet continue to shine. Each subsequent pass can strip away more material, gradually nourishing the black hole while extending the star's torment. These peculiar systems are natural laboratories for studying extreme gravity, showing me the fine line between survival and obliteration. To envision a star limping away from a black hole, its light flickering but still present, is to understand how delicately the cosmic forces of destruction and endurance are balanced. Galaxies are teeming with stars, but occasionally these stars are relocated. When two galaxies engage with one another, their central black holes can engage in a tug-of-war, capturing stars from each other. In other scenarios, stars on the peripheries of galaxies can be stripped away during close passes, taken by the gravitational supremacy of the other galaxy's core. Astronomers have even detected stars adrift between galaxies, likely victims of such encounters. Consequently, black holes, along with their host galaxies, function as cosmic plunderers, collecting and reallocating starlight across intergalactic space. This large-scale theft reminds me that galaxies are not isolated entities, but interacting, evolving systems. The stars I see in the night sky are not perpetually bound to their galactic homes. They are subject to the influence of greater forces, changing allegiance when gravity dictates. Galaxies are not static systems. They evolve, and gravity continually reconfigures their components. Dense star clusters orbiting near galactic centers can gradually spiral inward over billions of years. As they descend, their stars are either torn apart or assimilated by the central black hole. In this manner, black holes expand by consuming not just individual stars, but entire clusters. Observations indicate that some supermassive black holes attribute a significant portion of their mass to these slow, continuous feasts. This process also clarifies why the cores of galaxies are often dense with ancient stars, the survivors of these migrations. To imagine an entire cluster descending into darkness is to witness how galaxies recycle themselves, with black holes serving as engines of transformation. Though destructive, this process helps to establish the equilibrium between light and shadow at the hearts of galaxies. When a star gets too close to a black hole, it can be torn asunder in a tidal disruption event. Rather than being consumed whole, the star's material is stretched and drawn into a long, luminous stream. This stream circles the black hole, progressively spiraling inward and forming a disk of gas heated to millions of degrees. The process shines so intensely that it can outshine its host galaxy for months or even years. From Earth, these events manifest as abrupt, powerful flares, cosmic signals marking destruction on the most immense scale. Each disintegrated star is a reminder that even suns, as vast as they are, can be unraveled strand by gravity. These ethereal stellar streams curve through the void like ribbons, both beautiful and tragic traces of stars undone. Although black holes are often seen purely as agents of destruction, they can also facilitate creation. As matter descends into them, some black holes launch powerful jets of energy that travel outward across their galaxies. These jets compress clouds of gas, sometimes initiating the collapse necessary for new star formation. In this way, black holes function as both destroyers and midwives of creation, controlling the rate of stellar birth. Observations of galaxies reveal areas where star formation is particularly high, often associated with black hole activity. The influence of a black hole can reach tens of thousands of light-years, molding the life cycles of stars far from its direct vicinity. It is a remarkable paradox. The darkest objects in the universe can play a crucial role in disseminating new light. Not every star near a black hole is destined for destruction. Some establish stable orbits, circling at significant distances, held by gravity but far enough away to evade annihilation. In my own galaxy, astronomers have monitored stars like S2 and S4700 as they orbit Sagittarius A, the supermassive black hole at the center of the Milky Way. These stars travel at astonishing velocities, some exceeding 7,000 km/s, following elegant elliptical paths that validate Einstein's theory of relativity. To observe their orbits is to witness gravity in its most unadulterated form, with stars dancing around a void of infinite pull. Though they reside in hazardous surroundings, they persist, their courses dictated by the deepest wells of space-time. They remind me that not every star near a black hole meets a tragic end. Some live out their lives as close companions to cosmic darkness. When stars are in their infancy, they are frequently encircled by rotating disks of gas and dust. Within these disks, matter aggregates, colliding and merging to create the seeds of planets. Over millions of years, entire planetary systems take shape, molded by gravity and the influence of the central star. Astronomers have obtained images of such disks showing dark gaps cleared by nascent planets, confirming that I am witnessing creation in progress. My own solar system originated in such a disk about 4.5 billion years ago. Stars and planets are formed together, their destinies linked from the outset. To study these disks is to see the origins of worlds, a reminder that the planets I walk on and the moons that orbit them are natural consequences of the process that makes stars shine. The most massive stars emit such a powerful flow of radiation and stellar wind that they create cavities in the surrounding gas and dust. These bubbles can expand to dozens of light-years in diameter, glowing with ionized gas along their perimeters. Inside, the intense radiation clears out material, forming a hollow space around the star. When multiple massive stars form in proximity, their bubbles can combine to create vast superbubbles that reshape entire galactic regions. These structures are not merely beautiful, they affect the next wave of star formation by compressing gas at their edges. From Earth, I see them as luminous shells within nebulae, cosmic balloons inflated by the breath of giants. They demonstrate how stars do not merely inhabit their galaxies, but actively mold them, leaving signs of their power imprinted across space. When I, as an astronomer, observe a star's light fluctuating unpredictably, it does not necessarily indicate a change in the star itself. Sometimes the reason is orbiting dust that temporarily obstructs the light as it passes. A notable case is Tabby's star, which puzzled astronomers with its erratic dimming. The cause may be clouds of dust or debris drifting around it. These flickers remind me that the universe is not an empty expanse, but is filled with matter that can obscure, scatter, or filter starlight. To distant observers, my own sun might appear to flicker similarly if viewed through the dusty plane of the solar system. Such stars teach me humility as a sky watcher. What I see is always influenced by the space between myself and the light source. Hot, massive stars emit such powerful ultraviolet light that they ionize huge areas of adjacent gas, causing entire nebulae to glow. The Orion Nebula, for example, shines because a cluster of young, massive stars at its core floods the area with energy. Their radiation pushes back the gas, creating cavities and forming the delicate filaments of light and shadow I see in telescope images. Over time, this intense energy scatters the very material from which the stars were created, stopping further star formation in their immediate vicinity. In this manner, stars are both creators and destroyers, igniting their nurseries even as they consume them. These radiant sculptures remind me that light itself possesses force, shaping the architecture of galaxies on scales that span hundreds of light-years. Most stars reside within galaxies, bound by gravity into enormous families. However, not all remain. Some stars are ejected by violent events, such as close encounters with black holes or collisions between galaxies. These rogue stars drift alone in the intergalactic void, far from any home. Moving at hundreds of kilometers per second, they might spend billions of years in isolation, their light traversing immense distances without ever reaching another star system. Though solitary, they act as cosmic messengers, bearing clues about the forces that cast them out. The concept of a single sun wandering through the emptiness between galaxies is poignant, a reminder that even stars can be exiled, shining defiantly against the profound silence of space. The atoms that constitute my body were created long before I was born, deep inside the cores of stars. Fusion changes hydrogen into helium, and subsequently, helium into heavier elements like carbon, oxygen, and nitrogen. Massive stars extend this process, building silicon, iron, and more. When they perish, they distribute these elements into space, enriching future generations of stars and planets. Every breath of oxygen I take, every molecule of carbon in my cells, every trace of iron in my blood, all were once starlight. Stars are alchemists on a cosmic scale, transforming simple gas into the fundamental components of life. To look at the night sky is to see my own origin story, written in glowing furnaces, billions of kilometers away. I am, quite literally, the dust of stars carried forward into consciousness. At their very core, stars are massive fusion reactors. Gravity compresses hydrogen atoms so intensely that they merge to form helium, liberating energy as light and heat. This process, nuclear fusion, is the same reaction scientists aim to master on Earth for a nearly inexhaustible energy supply. The equilibrium between gravity pulling inward and fusion pushing outward maintains a star's stability for billions of years. Without fusion, stars would collapse under their own mass. With it, they shine across unimaginable distances, fueling the development of galaxies and enabling life on planets. When I see a star twinkling, I am witnessing the direct radiance of fusion, atoms combining in a continuous blaze that converts the raw material of the universe into brilliance. Stars are evidence that the cosmos itself is a kind of laboratory, operating on reactions that underpin everything I know. Hydrogen, the most fundamental and plentiful element in the cosmos, serves as the primary fuel for stars. Within stellar cores, pressures are so great that hydrogen atoms collide and fuse into helium, releasing bursts of energy with each reaction. This is the essential process that makes stars shine. Over time, the accumulation of helium alters a star's equilibrium, eventually causing it to expand, contract, or transition into new stages of stellar existence. In massive stars, fusion can continue beyond helium, producing progressively heavier elements. But it all starts with hydrogen. Every sunrise is a direct consequence of this quiet yet unceasing transformation, a sequence of reactions that has been ongoing for billions of years and will persist far into the future. The universe's light, warmth, and chemistry all originate from hydrogen being compressed into helium, one fusion reaction at a time. Stars are not eternal, but their demise is not the conclusion of the narrative. When stars detonate as supernovae or shed their outer layers, they enrich their environments with heavier elements. This gas blends with the interstellar medium, forming dense clouds. Over time, gravity draws these clouds together again, initiating the birth of new stars. Each generation of stars inherits the legacy of those that came before, developing more complex chemistry with each cycle. My own sun was formed from the remnants of previous stars, containing elements forged in ancient explosions. Future stars will one day be born from the remains of ours, continuing the sequence. It is a cycle of death and renewal that ensures the galaxy is never static. Stars live, die, and are reborn, weaving time together with their perpetual transformations. Not all galaxies generate stars at a uniform rate. In some, known as starburst galaxies, conditions are so intense that stars are created 100 times more rapidly than in the Milky Way. Collisions between galaxies often initiate these bursts, compressing gas clouds into ferocious waves of star formation. Entire regions blaze with young, massive stars, their radiation flooding space with energy. These galaxies shine with exceptional brilliance in infrared light, revealing the heat of countless new suns. But this intense activity is short-lived. After a few 100 million years, the gas is depleted or blown away, and the starburst subsides. What is left is a galaxy forever altered by that brief, chaotic period. To observe a starburst galaxy is to witness the universe in a moment of astounding productivity, a cosmic nursery operating at maximum capacity. Not all stars are created equal. Some begin their lives with dozens of suns nearby. My own sun was probably formed within a cluster, accompanied by numerous siblings. For some stars, this proximity is even more pronounced. In stellar nurseries, dozens or even hundreds of stars can form in close proximity, their gravitational forces pulling and twisting each other's orbits. Some systems result in multiple suns bound together, while others scatter their siblings over time. Being born in a bustling environment means stars can interact in dramatic ways, stealing planets, ejecting companions, or interfering with each other's development. Yet these are the same environments where the most complex chemistry develops, as shock waves, radiation, and winds mix materials. To envision a star's initial moments is to picture not solitude, but a vibrant, glowing nursery where dozens of suns ignite side by side, competing and cooperating in their earliest days. When stars comparable to the Sun deplete their fuel, they collapse to become white dwarfs. Although they are no longer powered by fusion, these stellar remnants stay hot, radiating stored thermal energy. Over billions of years, they gradually cool, becoming ever fainter. But the timescale is so immense that the universe itself is not yet old enough for any white dwarf to have completely cooled. Even deceased stars continue to shine, their soft glow marking the final resting places of suns that once shone brightly. Observing them enables astronomers to determine the ages of star clusters and trace the history of the galaxy. To see a white dwarf is to witness both an end and a form of persistence, a star's afterlife glowing quietly long after its fiery youth has concluded. Some stars come into being not in small groups, but in gigantic clusters. Globular clusters, for example, contain hundreds of thousands to millions of stars within tight spherical formations. These ancient assemblies orbit galaxies like satellites, remaining cohesive for billions of years. Their stars are among the oldest in the universe, relics from a primordial cosmic age. From within such a cluster, the night sky would be unbelievably luminous, filled with thousands of suns in every direction. Studying these clusters provides insights into stellar evolution, galactic history, and the limits of gravitational cohesion. They are natural laboratories where stars coexist in extreme density, showing me what stellar communities can be like at their most intense. To stand on a planet within such a cluster would be to see a sky set ablaze with starlight. Within dense star clusters, chaotic interactions are common. Stars exert gravitational pulls on one another, and when one detonates as a supernova, it can severely disrupt the gravitational equilibrium. Sometimes this chaos ejects stars outward at immense velocities, creating runaway stars that speed through the galaxy. These stars can achieve speeds of hundreds of kilometers per second, following solitary paths far from their origins. Astronomers can recognize them by their movement, often finding them moving away from clusters or supernova remnants. Runaway stars tell a story of violent beginnings, of gravitational chances that determined their destiny. Though exiled from their crowded homes, they carry the memory of explosive origins, their speed a lasting testament to the forces that set them adrift. At the core of the Milky Way is Sagittarius A, a supermassive black hole with a mass approximately 4 million times that of the Sun. Remarkably, stars orbit it directly. Astronomers have tracked these stars for decades, observing them follow elongated paths around the invisible behemoth. One star, S2, approaches so closely that it orbits the black hole at speeds over 7,000 km/s. Monitoring these orbits offers one of the clearest confirmations of Einstein's general relativity, as the starlight bends and redshifts in ways his equations predicted. These stars exist in a dangerous environment, yet they survive, shining defiantly as they circle a void of immense gravity. To watch them is to see a cosmic ballet at its most extreme, suns dancing on the very brink of darkness. Black holes do not only consume stars, they also bend the space that surrounds them. Stars located nearby often have their paths contorted into unusual orbits. Some may be catapulted around the black hole at incredible speeds, while others may spiral inward toward their demise. Even stars at safer distances experience the curvature of space-time, following trajectories that diverge from Newtonian predictions. Observing these movements has provided astronomers with a natural laboratory for testing the boundaries of physics. In the center of the Milky Way, warped stellar orbits demonstrate the immense power of Sagittarius A without needing to see it directly. For distant galaxies, stars bent into tight swirls confirm the existence of supermassive black holes that are too faint to be observed otherwise. The warping of stars is both a map and a signature, the unseen fingerprint of gravity at its most intense. My Sun feels immediate and recognizable, but the next closest star is at an unimaginable distance. Proxima Centauri, a part of the Alpha Centauri system, is over 4 light-years from Earth, roughly 40 trillion kilometers away. If a spacecraft could travel as fast as the New Horizons probe that departed my solar system, the trip would take almost 80,000 years. Yet, on a cosmic scale, Proxima is my closest neighbor, and it even harbors at least one planet in its habitable zone. To gaze at the night sky is to comprehend that even my nearest stellar companion is separated by a chasm so vast that light itself requires years to traverse it. This viewpoint makes the Sun feel both more valuable and less exceptional. Just one star among many, but also the one that supports my fragile existence. The Sun may command my skies, but it represents just one of hundreds of billions of stars within the Milky Way. Each of those stars has its own history, some solitary, some in pairs, some with planets, some fated for explosive ends. The sheer quantity implies that for every star I know, there are billions more quietly burning throughout the galaxy's spiral arms. Many are smaller red dwarfs that burn dimly for trillions of years. Others are giants that blaze thousands of times more brightly than my Sun. From Earth, I see only a fraction of them, even on the darkest nights. To envision the Milky Way in its entirety is to picture a luminous disk of light so vast that my Sun is a single particle in its expanse. My star is both common and unique, a typical light, yet the one that makes my world possible. When I gaze upward on a cloudless night, almost every star I see is a member of my own galaxy. They are the local residents of the Milky Way, distributed across its spiral arms. Only a few of the brightest specks of light, like those in the Andromeda Galaxy, originate from beyond. Everything else, Orion's belt, the Pleiades, the stars of the Big Dipper, is local in cosmic terms. The Milky Way is so dense with stars that, when viewed from dark locations, it appears as a glowing band across the sky, the combined light of millions of suns. What seems to me like a personal canopy of twinkling lights is, in fact, a cross-section of a vast rotating disk of stars. To remember this is to feel both humbled and interconnected. The night sky is not random, but a view into my galactic home. Galaxies are not static entities. When they interact or pass closely, their gravitational forces pull and strain everything within them. Stars, once securely held, can be cast out into intergalactic space. These rogue stars drift alone, no longer connected to any galaxy, carrying their light across the immense void. Some may have planets with them, orphaned worlds journeying together through the emptiness. These stellar exiles can travel for billions of years, never to return to a galactic home. Observations indicate that intergalactic space is not truly empty, but is dotted with such wandering stars. Each one is a reminder that galaxies are living, evolving structures, and that the bonds holding stars together can, in the right conditions, be severed by the relentless force of gravity. When stars like my Sun approach the end of their existence, they swell into red giants and eject their outer atmospheres. These layers expand outward into space, creating glowing shells of gas illuminated by the remaining core. The outcome is a planetary nebula, a misnomer for a beautiful structure that has no relation to planets. Instead, these nebulae are cosmic grave markers, luminous tombs that signify a star's demise. They can endure for tens of thousands of years, painting the sky with delicate forms and colors before dissipating into interstellar dust. Well-known examples like the Ring Nebula or the Helix Nebula show me the Sun's probable destiny billions of years from now. Although they signify endings, planetary nebulae also enrich space with new material, ensuring the cycle of creation persists. When Sun-like stars perish, they contract into white dwarfs, which are dense, Earth-sized remnants that no longer perform fusion but continue to radiate residual heat. They are the smoldering embers of once living stars, shining faintly for billions of years. A teaspoon of white dwarf material would weigh tons on Earth, a testament to the immense pressure that maintains them. Over time, they cool and diminish, eventually becoming black dwarfs, though the universe is not yet old enough for any to exist. White dwarfs are astronomical fossils, preserving information about the age and history of the galaxy. To see one is to witness both a conclusion and a quiet perseverance, the final echo of a star that once shone brightly in the sky. Not all stars share the same destiny. Smaller stars, like red dwarfs, fade away gently, cooling into white dwarfs without significant event. In contrast, larger stars often perish in cataclysmic explosions known as supernovae, scattering their outer layers across space in dramatic displays of light and energy. These cataclysms forge and distribute heavy elements, seeding galaxies with the components for planets and life. Some of the most massive stars collapse into neutron stars or black holes, leaving behind some of the most peculiar objects in the universe. The variety of stellar deaths mirrors the variety of stellar lives. Whether quiet or cataclysmic, every end is part of the cycle that drives galactic evolution. In every case, the death of a star is never just an end. It is the beginning of something new. Observing the night sky reveals a sense of both permanence and transience. Stars appear constant, their constellations fixed. Yet over time, stars are born, live and die, altering the celestial tapestry. Nebulae emerge where new stars ignite, supernovae flare where old ones collapse. Clusters separate, galaxies collide, and rogue stars wander into the void. Even my Sun is temporary, destined to one day expand and fade. Stars remind me that the universe is not static, but is alive with change. Every twinkle is a moment in a continuous story that spans billions of years. To see them is to glimpse both eternity and flux, the vast, slow rhythm of the cosmos carrying me forward in its endless cadence. Thank you for accompanying me on this tranquil exploration of the stars. I have journeyed from their fiery origins in immense clouds of gas through their long and stable lives to their quiet embers and explosive finales. Throughout this journey, I found reminders that stars are not merely distant specks of light, but are the architects of everything I know, the creators of atoms, the keepers of time, the narrators of the cosmos. It can be humbling to realize that the very blood in my veins, the air in my lungs, and the bones in my body were once created in the cores of ancient suns. Stars lived, died, and dispersed their remnants so that I could one day exist here, breathing quietly beneath their light. Every night sky is not just a spectacle, but a chronicle of creation written across space. As I conclude this narrative, there is no need to retain all the specifics. You can allow them to float away like stardust in the wind. What is important is the feeling, the calm immensity, the sense of being small yet profoundly connected. You are a part of this universe, woven from the same material as the stars themselves. If you found solace here, I would be grateful if you considered liking or subscribing or sharing a thought in the comments below. It helps others find this channel, one peaceful soul at a time. But for now, nothing more is required of you. Simply permit your breath to slow. Let your body relax and feel the burden of the day dissolve. The stars will continue to burn, the galaxies will continue to revolve, and you can just rest. Somewhere out there, a star is shining whose light will not reach Earth for thousands of years. By the time it does, you will have had 1,000 dreams, and the world will have rotated countless times. The stars remind me that time is immense, but also gentle, a flow to which I can surrender. So, let yourself drift, borne by that current, into the quiet darkness. Sleep well. Dream profoundly, and know that the same starlight that illuminates the cosmos has always resided within you. Good night.